Are you sharing, Rafiqul?
Yeah, this issue.
Okay. Okay, no issues. We have your slides. We can also project it. Okay. If, if it doesn't work when you present, we can also project it. Okay. Let's then start. Now I request Rohini and Nilima to uh, take over this session as chairs, and we can start.
Okay, thank you, Bedanga. So, good afternoon, everybody. This is the Rahul Basu Memorial Best Thesis Award session. And we are going to have 5 talks by the 5 prize winners. But before that, I would like to invite Dr. Nilima Gupte to say a few words giving the background of the award. So, Nilima, you are on.
Yeah, can you hear?
Yeah, we can hear you.
You can hear me.
Yeah.
So, welcome everybody, and welcome to the award ceremony of the Rahul Basu Memorial Award. And this award is constituted in the memory of my husband, Professor Rahul Basu, who many of you know, especially all the committee members do know him. In fact, as it happens in every award session, there has been at least 1 or 2 awardees who knew him because he had taught them in various Cirque schools or in various other contexts. So I think even now we have not lost living memory of him. And this award was constituted in his memory because we noticed I wanted to institute something which will, in fact, not just keep his memory, but also contribute constructively to the high energy physics community. And especially, I wanted to constitute something which will provide a forum for young people, for the younger members of the high energy physics community. And what Professor Rohini Godbole and I, who helped me constitute this award and have it set up through the Indian Physics Association, thought was that it would be really nice if this could be the award for the best PhD thesis in high energy physics. And Professor Basu was very proud of the professionalism as well as the level of PhD thesis in his area. And in all the years, we have now given this award 5 times. And I have to say that the way in which I'm obviously not an active member of the award committee. I am just the IPA nominee, although I'm a theoretical physicist. So I do understand what goes on. And I have been highly impressed by the level of thesis which comes in, by the level of the awardees, and also by the huge amount of effort and professionalism which the award committee puts into the process. Okay. So as I said, Professor Rohini Godbole and the Indian Physics Association helped me set up this award. I'm truly grateful to them. Professor Sunil Mukhi and Professor Bedang Das Mohanty have been the first 2 chairs of this committee, and they have contributed to the highly professional way in which this process has been set up. And I'm highly grateful to them also. And most of all, it's the awardees and their enthusiasm and the high level of their thesis which have contributed to the prestige of this award. And I think without further ado, I'd like to pass this on to Professor Mohanty so he can say something about how the awardees are identified by a fairly rigorous process. Thank you. Yeah, Rohini, you could pass this on to Bina. Hello.
Thank you, Nilima, for having given this nice introduction about the award. So Bedanga Mohanty, who is the chair of the Rahul Basu Memorial Award Committee, I will now request him to tell us briefly about the process that was used to arrive at this Rahul Basu Memorial Best Thesis Award. And let's just have Vedanga tell us this. Vedanga?
Yeah.
Stage is yours.
Thank you. Thank you, Rohini. Thank you, Nilima. Okay, so this is about the IPA Rahul Basu Best Thesis Award in High Energy Physics. The winners receive a cash prize, currently 25,000, and a citation. Go to the next one. This award, as you heard, which is coordinated through the Indian Physics Association, is given for the two most outstanding PhD theses from India across all areas of high energy physics, both theoretical and experimental, during a 2-year period. 2012, 14, 16, 18, we had already completed, and this year we are doing it in 2020. This is in memory of Professor Rahul Basu. These are the committee members: Sorendu Gupta, Sunil Mukhi, Jim Libby, myself, Nilima Gupte, Debashish Ghoshal, Sunanda Banerjee, Seema Sharma, and Rohini Goodwale. We received 27 nominations. 2 have been awarded the best thesis and 3 have got honorable mention. The committee really deliberated in several stages. And so the committee, on behalf of the committee, would like to congratulate all candidates who were nominated, and we're very happy to note that several interesting work in the field of high energy physics is being carried out in India. The committee also felt that many of these of the theses received contained very high quality work, and the decision was not at all easy. The committee also places on record the sincere gratitude and thanks to several colleagues from outside the committee who assisted in the evaluation process. So this is the 2 winners. Dr. Reshmi PK from IIT, did her PhD from IIT Madras. This is the certificate. She is going to talk about her work on measurement of CKM angle and in experiments. Then this is for the theory, Manibrata Sen from TIFR, whose thesis was on new aspects of supernova neutrino flavor conversions. The honorable mentions, Chandra Dai from TIFR on entropy production and thermal fluctuations in higher order dissipative hydrodynamics. Dr. Rafiqul Rahman, whose thesis from IISER Kolkata, whose thesis was study of anomalous gauge boson self-couplings and the role of spin-1 polarizations. And Dr. Suman Chatterjee, whose work was on jets as a probes for precision measurements and candles of physics beyond standard model from TIFR. So on behalf of the committee, congratulations to all the 5 very, very deserving colleagues now. Yeah, thank you.
Thank you, Vedanga, for this very succinct and nice presentation. So I may add here 1 or 2 sentences of my own, that this time, to one of the students from IISc, I had said, wouldn't it be a good idea to nominate your thesis? And he told me, I have seen the thesis of the earlier awardees, and it's not just enough to have good research, but it is also necessary to write the thesis, which puts the work in the context. This is what I have realized. And therefore, that student particularly said, I don't think my thesis is fit to be nominated for the award. So somehow I think over the years, this tells me that the award has, the thesis that awards have got, this particular statement by the student tells us already about the stage, a good stage at which this award has reached. The other one that I wanted to say was that I was recently in the GBM, and people were bemoaning the fact about how different awards that have been set up, the funds are not perhaps enough to be sure that the appropriate award can be granted. And luckily, this award is the only award which was completely in good shape. So I want to thank Nilima for that. And now we will begin the physics part of the ceremony. And each of the speakers will have 20 minutes. And I will tell you already, all of you, that I will give a 5-minute warning. And then you should wrap up your talk in the first, in those 5 minutes. So I'm inviting first Chandra Dai from TIFR, who finished his PhD from TIFR. And he's going to talk about entropy production and thermal fluctuations in higher order dissipative hydrodynamics. So can we have his share? Can Chandra Dai, can you share the screen?
Yes, sure. Is my screen visible?
Your screen is visible, and I will give you a 5-minute warning, okay?
Okay.
From when you begin, okay?
Okay, yeah.
That means from now. Thank you.
Okay. First of all, I am greatly honored to be a recipient of honorable mention, and I thank the organizers for this opportunity to speak at this prestigious ceremony. So today I will be talking about entropy production and thermal fluctuations in higher order dissipative hydrodynamics. So relativistic hydrodynamics has become the workhorse of describing the intermediate stages of heavy ion collisions, especially the evolution of quark gluon plasma. So hydrodynamics is based on a description using macroscopic parameters like temperature, chemical potential, flow velocity, and so on. And originally, ideal hydrodynamics was used to describe the final state observables. And the problem was ideal hydro is applicable when a system is in perfect local equilibrium. So whenever system deviates from local equilibrium, dissipation has to be included. The thing is, formulation of dissipative hydro is still not well settled, and I'll talk about it. So in the first part, I'll talk about certain aspects of formulations of hydro, and especially focus on the entropy current to quantify how the system that we are looking at deviates from local thermodynamic equilibrium. So relativistic hydrodynamics is based on conservation of the energy momentum tensor and any other charge currents that may be conserved in the system. So for ideal hydrodynamics, there are 5 unknowns: the local energy density, the local pressure, and the 3 components of the flow velocity. Delta U mu is a projector operator. And we have 4 equations plus an equation of state which relates the pressure to the energy density. So the equations of ideal hydro are closed. Now the simplest way of including dissipation would be to add a shear stress tensor pi mu nu to the ideal part. Now pi mu nu has 5 independent degrees of freedom. And thus we already see that in order to close the system of equations, we require 5 more equations, and we need to get it from somewhere. So in this talk, I will be talking about deriving shear stress tensor from relativistic kinetic theory. Okay, so kinetic theory is based on a description using a single particle distribution function, which gives the mean number of particles in a phase space volume element. So the strategy is to obtain this distribution function to some approximation and then integrate out the particle degrees of freedom to obtain macroscopic quantities like T mu nu or the entropy current or any other such quantities. Now the evolution of the single particle distribution function is governed by the Boltzmann equation, where the right hand side denotes the collisional kernel, which takes into account the effects of interactions. So usually this collisional kernel takes into account binary collisions, but this is an integral differential equation and can be notoriously hard to solve. So instead of a of the full blown collisional kernel, we solve a simplistic version of it, which is known as the relaxation time approximation, in which the distribution function relaxes to the equilibrium value over a time scale that is controlled by the relaxation time. Now, it's still hard to solve this equation exactly, and we employ an approximation scheme to solve this equation. So what we assume is the ratio of the mean free path and the ratio of the mean free path to the gradients of the system are small. That is to say that tau r times del x mu is a small quantity. And this is exactly the Knudsen number of the system. So basically, the Boltzmann equation can then one can associate a power counting scheme given by this Knudsen number, and then can employ a systematic perturbative series based on expansion in this order parameter. And then the strategy is to solve the Boltzmann equation order by order. For example, the 0th order is the equilibrium. The first order correction contains one derivative of the equilibrium function. The second order contains two derivatives, and so on. And once we obtain the distribution function to some approximation, we integrate out momenta, the particle degrees of freedom, to obtain macroscopic variables. So in the same way, because we approximately solve the distribution function, then we plug it in the expression for the entropy forward current. And in this work, we solved it to third order in the velocity gradients. So this was the first term is the equilibrium correction to the entropy current. Thus, these are the second order corrections, and these are higher order corrections. So the important part of this is to note that the entropy density in the local rest frame, the first correction to the entropy density is quadratic, and one can show that this term is less than or equals to 0. And this is expected because whenever a system deviates from perfect local equilibrium, then the entropy is less than the equilibrium value of the entropy. Interestingly, our derivation shows that there can be non-vanishing entropy flux even in the local rest frame of the fluid. So even if one is co-moving with the fluid, there can be some diffusion of entropy. And this was not observed till order 2 and appears only at higher order in the gradient expansion. So the key point to take is entropy flow is not necessarily along energy flow. So given these derivations, we look at some applications. So we consider a boost invariant expansion of a medium, which is a good description of the heavy ion collision dynamics at the early stages after the early stages of the collision. So in Bjorken, the system expands along the z direction. There is no transverse dynamics, and the symmetries are manifestly expressed in the Milne coordinate systems, which are the lines of constant tau and constant eta. And here we plotted the evolution of the shear stress tensor, the pressure anisotropy, the entropy content of a fluid, and the ratio of the full entropy density to the equilibrium entropy density. And in all the four figures, the red dotted lines describe the hydrodynamic approximation I've been talking about. And we compared it with the exact solution of the Boltzmann equation, which are shown by the green lines here. I will not talk about the other model that we used here. So the common theme in all of these plots is that the system starts from local equilibrium, but because of rapid longitudinal expansion, the system falls out of equilibrium. And then as the longitudinal expansion rate decreases, the system again attains local equilibrium. An interesting feature is that from panel D, one can see that although the entropy deviates from its equilibrium value to a large extent, the hydrodynamic description for the pressure anisotropy or shear stress matches quite well with the description given by the exact Boltzmann equation, meaning that hydro can be applicable even in regimes when the system is far from equilibrium. Then we go to another flow profile, which is transverse dynamics, which is known as Gupser flow. So Gupser flow is just like Bjorken flow, it has a longitudinal expansion. But what happens is at late times, the transverse dynamics begins to dominate, and the system eventually expands so fast in the transverse direction that particles cannot interact and the system essentially free streams. And we looked at the similar quantities in Gupser coordinates. So here the x-axis rho is the equivalent of the Gupser time. So here also one sees that initially the system goes towards longitudinal free streaming, then there is some local equilibration, and then the system starts to go towards free streaming in the transverse direction because the PT here goes to 0. Interestingly, the entropy content of the fluid to start with does not change too much because the system is free streaming. Then it increases, but then even at later times, the entropy content does not change too much because the system again moves towards a free streaming regime. So entropy is not being produced. However, it is clearly seen that the entropy strongly deviates from its equilibrium value, suggesting that the system is nowhere close to equilibrium. And this is one example where one sees the breakdown of Chapman-Enskog hydrodynamics because of far from equilibrium dynamics of the system. So I'll quickly go over to the second part, which would be connected to entropy. And here I would be talking about statistical fluctuations of macroscopic quantities. So let us consider a system whose macro states are labeled by these quantities. The probability of the system being in this macro state is given by the number of microstates that are available to the system. This is counted by the entropy. So we know in thermal equilibrium, all these quantities are close to their mean values, which actually maximizes the entropy. And we are interested in looking at small fluctuations about the mean value of these variables. So because the entropy is a maximum at XA bar, the first correction is quadratic in the deviations from equilibrium quantities. So, and from here one can calculate the 2-point functions of these perturbations, and these are related to these coefficients that appear in the expansion of the entropy. Now, given this, we can ask that, okay, if there is a fluid in global equilibrium, it has some energy momentum tensor, some entropy, then we can just reproduce this calculation for that fluid and ask that what is the probability that there is some fluctuation of the temperature or the flow velocity by amount delta T or delta V and so on. And when one does this calculation, one sees that there are the mean squared of the fluctuation of energy density is given by this, and the mean square of the part of the fluctuation in velocity is given by this formula. But ordinary hydrodynamics do not take care, do not consider any of these fluctuations. These are perfectly deterministic equations. There are no concepts of mean square of these quantities. So what can we do to ordinary hydrodynamics so that these are taken into account? The answer is given by Langevin type of equation. So when we describe a Brownian motion of a particle in some medium, then we know that there is a drag force to the momentum, but we also know that there is a mean square of this quantity, which is given by the mass of the particle and the temperature of the background medium. And this can be reproduced only if we add a diffusion term or a noise term to the evolution equation, and then constrain that the 2-point function of this noise is given by a certain form. So then we can nicely reproduce the quantities that we are looking for. And this approach can then be extended to a multivariable problem when there are many quantities, small x's. And basically we have to solve linearized equations, adding a noise term, and the 2-point function of the noise term will be constrained by the matrices, the gamma AB, which are also known as the Onsager coefficients. So this is a strategy. We have to compute S dot, identify the so-called driving forces and the independent variables, and from there get to a form of these Onsager coefficients, and this will give us 2-point or the autocorrelation function of the noise terms that must be added. So then we looked at higher order hydrodynamics. So this was a 2nd order evolution equation for the shear stress tensor that I was talking about in the first part of my talk. We have an expression of the entropy for current up to 2nd order in dissipative quantities. And from there, we can just compute the divergence of the entropy for current. And then implement the framework I just talked about. We have to identify what are the independent, what are the generalized forces and what are the independent variables in this problem. And it is from this expression here, it is straightforward to identify that the role of the small XA dots can be played by the shear stress tensor, and the role of the generalized forces, which basically multiply the small XA dots, are basically the terms in the brackets here. Okay. And once we know that, just as we did in the case of many single variables, we have to add a noise term to this part. So in complete analogy, we add a noise tensor to the shear stress tensor part. And basically the goal now is to determine what is the Onsager coefficient matrix that appears in front of these variables. There are certain symmetries that govern the form of these gamma matrices. And once we take that into account, we obtain a new kind of dissipation relation in our work. So all the terms that are denoted by red here are the new terms that we obtain because of taking into account a higher order definition of the entropy. So now, given that we have a framework, we look at certain applications. Okay. And the first one is we take a fluid in global equilibrium, that is a static fluid. So in this case, there is a noise term that has been added to the shear stress tensor part, and the autocorrelation of the noise is given by the fluctuation dissipation relation that I just derived. And for simplicity, I work in 1+1 dimensions here. There is a z coordinate, and look at linear perturbations along around the equilibrium, the global equilibrium, which is basically a system that is at complete rest. And for this case, the linearized equations can be solved exactly analytically, and we obtain the 2-point functions of the energy density, for example, are given by this form. This exactly matches with the statistical physics expectation that I just talked about in 2 slides ago. And in addition to equal time correlations, there are unequal times correlations also that are induced in the fluid, and we find that these are induced solely by propagating sound modes. And if one includes viscosity in the framework, then what happens is these delta functions are smeared, and which basically means that viscosity dampens the propagating correlations in space and time. Okay, so this was what I just discussed about was the case in a static fluid. It was physically motivated, but also quite simple to understand. But what happens when the background fluid is expanding, which is the case that one has in heavy ion collisions? So we look at a fluid that is expanding in the boost invariant fashion along the beam axis, and so basically we consider Bjorken flow and then perturb around a background solution to Bjorken flow. Okay. Interestingly, unlike a static fluid where the dispersion relation is linear, in Bjorken flow, when we solve the perturbation equation, one finds that the dispersion relation is nonlinear and also has a dissipative like dispersion. So this was also known before, and this is a crucial element which would.
You have only 5 minutes now. Okay.
Yes. Okay. Thanks. Yes. So this dissipative type dispersion relation would be crucial in something that I will just discuss now. Okay. This was not present in a static fluid. So as I just said, that whenever we looked at fluctuations in a static fluid, at equal times there was no long-range correlations, there was only short-range singularities. But in case of an expanding medium, we find that because of nonlinear dispersion relation, even at equal times, there is a regular part as well as a singular part. So these are the short-range parts which also exist in a static fluid, and these are the ones which arise because there is a background expansion, and the dispersion relation is nonlinear. Okay. So given this, so far we have been talking about 2-point correlations of hydrodynamic variables. But what is finally observed in detectors are correlations of particles. So we then looked at how to convert the 2-point functions of hydrodynamic variables into 2-point functions of final state particles. So basically we used a Cooper-Frye framework, which is a method to convert fields, the hydrodynamic fields, to particles. And using this, one can compute the 2-point correlations of rapidity of particles. And basically what this expression physically means is how 2-point functions in thermodynamic variables get converted into 2-point functions of final state particles. Okay. And then we finally show here the 2-point rapidity correlation of pions as a function of the rapidity gaps of pions in different hydrodynamic frameworks. In all of these cases, we see that there is some long-range correlation, and this long-range correlation basically arises because the background fluid is expanding. If it was a fluid in static equilibrium, we would just observe some short-range peak. And so in variety of these dissipative frameworks, we see that there might be long-range correlations in 2-point functions of pions, which can be sensitive to the evolution of the medium, like equation of states, which we show here because the patterns change slightly, and also to the amount of viscosity that is in the medium. So the key points to take here that the short range peak decreases with inclusion of viscosity in background, and correlations become short range with including a different equation of states. So all of these here are ideal, and these we consider lattice equation of state. So this was in Bjorken, and in Bjorken, the 2-point rapidity correlations depended only on the rapidity difference of two particles and not on the individual rapidities. But we then also considered more realistic medium in which there is a 1 + 1D expansion of the fluid. And here you see that the 2-point functions, the 2-point correlation functions of pions depends not only on the rapidity difference, but also on the different individual rapidities of the particle. So this can be a way of seeing how important is 1 + 1D dynamics, or how important it is to move away from Bjorken dynamics when we simulate realistic collisions. And here also we find that correlations become short range with the lattice equation of state. So I summarize here, we derived a higher order evolution of entropy forward current in conformal hydro using kinetic theory. We obtained higher order evolutions for a flow profile, scoop cell flow, and using our derivation of entropy forward current, we derived a fluctuation dissipation relation in second order hydro. We analyzed the effects of thermal fluctuations in an expanding medium on particle correlations. And we would like to extend at some point this study of fluctuations to regimes that they may not be treated perturbatively. That's it. Thanks. Yeah. So, yeah, I thank my PhD supervisor, Professor Subrata Pal, and different members of TIFR, to whom I am very grateful for. Yeah. Okay.
So, very good. Thank you very much for a very nice talk. And if at all we are left with time, I would come back and invite questions if there is time. So thanks again, and congratulations once again. So now can you stop sharing the screen,
Yes.
please? And we will move to the next talk, which is by Manibrata Sen. And he was a PhD student at the Tata Institute. And as you have heard, he is one of the winners. And he is going to now tell us about some new aspects of supernova neutrino flavor conversions in the standard model and beyond. So Manibrata, the stage is yours. And again, I will give you a warning after 15 minutes.
Okay,
so
thank you.
Please go on. Please go on.
So can you see my screen?
Yeah, we can see your screen and everything is perfect. We can
Okay,
hear you well. Just start. Okay.
Okay. So thank you very much. So I'm Manibrata, and today I'll be talking about part of the work that I did in TIFR as a part of my doctoral thesis titled New Aspects of Supernova Neutrino Flavor Conversions in the Standard Model and Beyond. So this talk will be divided into two parts. The first part will talk about the kind of physics that exists within the standard model, and the second part will go beyond the standard model and look for different probes of new physics. So before I start, I would like to give a big thank you to the members of the Rahul Basu Memorial Award Committee for considering me for this great honor. And this has been a matter of a great honor for me. And secondly, I would like to thank my advisors at TIFR, Professor Amol Digga and Professor Basudev Dasgupta, without whose guidance it would have been impossible to be at this stage right now. And I would also like to thank everybody at TIFR, all faculties, colleagues, and staffs with whom I've interacted for all their support. So let's begin. Since this is a supernova talk, I would like to give a lightning quick introduction about the mechanism of a core collapse supernova. So essentially, we are looking at massive stars, more than 8 or 10 solar masses, which at the end of the hydrostatic burning phase is mostly left with a very massive iron core, which keeps on growing in size as more and more matter accretes on top of that core. Now, as the core becomes more massive than the Chandrasekhar mass limit, it becomes unstable due to its own weight, and then it starts collapsing. Now, as the collapse continues, the density of the central core keeps on increasing until it reaches a point where nuclear densities are reached, at which point it becomes very stiff and then it resists a collapse. This leads to the formation of a shock wave, which propagates outwards. At the same time, a large number of neutrinos are also emitted in the same process. Now, it is believed, although we don't still have any concrete proof of it, that these neutrinos play a major role in causing a successful explosion for a core collapse supernovae. The crux of the matter for a particle physicist is that in this kind of a scenario, a large number of neutrinos are emitted. It's like almost all the information of the supernova is converted in the form of neutrinos and it's shown towards the Earth. So in order to understand the mechanics of a supernova, it's extremely important to understand the governing dynamics of neutrinos as they propagate through the dense material. So how is neutrino flavor transport inside a supernova different from usual neutrino flavor transport inside the sun or inside the earth? It essentially deals with the fact that inside a supernova or any other compact objects, there are huge sources of, there's a huge density of neutrinos that also exist. So while neutrinos, as they propagate through the sun or through the earth, essentially experience an extra matter mass-like effect due to interactions with the background matter, essentially through Feynman diagrams of this form. So a nu can interact with the background electron via this process or this kind of a process. Inside the sun, there are also additional interactions because the neutrinos can forward scatter off themselves through essentially these kind of processes. And in the neutrino flavor space, this kind of term can be flavor off diagonal simply because an electron neutrino can scatter off a muon neutrino through this kind of a process. This is what makes the entire problem extremely complicated, because now the entire problem becomes coupled. In order to understand the propagation of a certain neutrino of momentum P, you need to understand the propagation of all other neutrinos of momentum Q, for example. And this makes the whole problem very complicated and also very interesting. So the idea is, how do you study this kind of a process? How do you go about this process? So the easiest thing is, instead of studying a single neutrino, it helps if you look at the neutrino ensemble as a whole, because it gives you the behavior of the neutrino fluid as a whole. So the best way to go about it is to define a neutrino flavor density matrix, which is essentially defined in this form. And in this entire talk, I will be restricting myself to 2 neutrino flavors. The generalization to 3 flavors is relatively straightforward, and all the important physics will be captured by 2 neutrino flavors. So in this density matrix, this is a complicated 7-dimensional object consisting of 3 dimensions of position, 3 of momentum, and 1 of time. The diagonal elements essentially give you the information about the net flavor content. So throughout the talk, when I refer to a neutrino as nu x, I refer to it as I specifically mention non-electron neutrino. So anything which is a muon neutrino or a tau neutrino. So the diagonal elements give you information about the net flavor content, whereas the off-diagonal elements essentially gives you the overlap between the flavors. So they encode flavor coherence. So with this density matrix, one can write down a kinetic equation of this form where H is the Hamiltonian. Now, since we are talking about 2 cross 2 matrices, we can also expand them in the Pauli basis, where essentially you can write the density matrix as a trace times the identity matrix and some vector, which we call the polarization vector, times the sigma matrices. And similarly, you can expand the Hamiltonian also as some vector in the same basis. And when you plug this into this equation, you can get an equation for a precession of a vector. So these polarization vectors essentially can precess about the direction of the given Hamiltonian. And these precession vectors actually encode information about oscillation of neutrinos. So these are 2 different formalisms which will come in handy as we try to study flavor oscillations of supernova neutrinos. So the next big question is, how does the Hamiltonian look like? So as we discussed before, the Hamiltonian essentially will have 3 terms. There will be one term which is given by omega, which essentially encodes vacuum oscillation information. So this is proportional to the mass square differences of the neutrino, the energy, and the mixing angle. Then you would have a term given by lambda, which is essentially encoding the neutrino interactions with the background matter. So this is proportional to the electron number density in the medium. And finally, the most important term in our context is this term, which essentially encodes the neutrino-neutrino self-interactions. And naturally, it's proportional to the neutrino number density. And as you can see, the Hamiltonian for a neutrino of mode P essentially depends on an integral over all other neutrinos of mode Q. This is what makes this entire problem nonlinear and coupled. Now, the typical scales of the problem follow this kind of a hierarchy where mu is much, much larger than omega. And in a system where these neutrinos are tightly coupled, one can experience something called collective oscillations of neutrinos. So what I mean by this is that when the neutrino density is extremely high, it's possible that what this term does is it causes a significant fraction of the neutrinos to change flavors coherently with each other instead of individual flavor conversions. And these kind of collective oscillations can be much larger than even the resonant MSW conversions that we talk about. And this can give you very, very interesting effects. So I will, my PhD thesis worked on essentially one of these kind of collective oscillations of neutrinos, which goes in the literature by the name of fast flavor conversions of neutrinos. So the first of the talk essentially deals with physics within the standard model, plus the additional fact that neutrinos can oscillate among themselves. So what are these fast flavor conversions? These are very, very rapid flavor conversions, which essentially grow with a rate which is proportional to the neutrino number density. So deep inside the supernova, where the neutrino number density is very high, these oscillations are super rapid. If you look at this right-hand plot, which essentially plots the nu E survival probability, It shows that these kind of conversions can cause the NUEs to undergo flavor conversion within tens of nanoseconds. It's that fast. The more intriguing part is that these kind of flavor conversions are almost independent of the neutrino masses and mixing. And they can happen very, very deep inside the supernova near the neutrino decoupling region. So what causes these kind of flavor conversions? The main idea is depends on the fact that different flavors of neutrinos actually have different points of decoupling. So instead of a very nice picture like this, where all the neutrinos of different flavors decouple at the same point, one needs to adopt a picture where the neutrinos of different flavors essentially decouple at different points, simply because they have different energy and hence they have different cross sections. So they would have different points of decoupling. So any point near the neutrino decoupling region would look somewhat like this, where let's say the NUEs which decouple the last would still be collisional and then would have more of an isotropic distribution as is given by the blue lines out here. Whereas the NUE bars, which might have decoupled a little bit earlier, will be more forward peak. So there will be more NUEs in the forward direction as opposed to the NUE bars. What this does is this causes an anisotropic angular distribution for different flavors of neutrinos. And it is this anisotropy in the angular distribution that gives rise to these fast conversions. Now, you can simulate this entire problem numerically and try to solve it, and it's complicated. What we want to understand is that, is it possible to get a handle on these flavor conversions analytically? Is it possible to get an intuitive understanding of what these flavor conversions are? In order to do that, instead of looking at the survival probability, it helps if you're looking at the off-diagonal elements of the density matrices. So what I plot out here is the log of the off-diagonal elements as a function of time. And let's focus on one of these lines, let's say the blue line. So what the interesting thing that you see is that as the survival probability starts departing from 1, these off-diagonal elements start off as a very tiny quantity, but as the probability starts departing from 1, it starts growing exponentially. Mind you, this is a log plot, so any exponential growth looks like a linear curve. So the idea is, since it starts off as a very tiny value, you can linearize the nonlinear Hamiltonian in these off-diagonal elements, and then you can look for exponential runaway solutions of these off-diagonal elements. This would, if you get such a solution, it would signal that the problem has an instability in it, and then you can interpret these collective oscillations as an instability problem. Also, this allows you to predict the growth rates of these modes, which are essentially the slope of this linear line out here. This is what we use throughout the thesis to calculate the growth rates of these collective oscillations. So now, depending on the situations that we talked about, we can take different toy models to try to implement this kind of a physical setup, where let's say the NUEs are more or less isotropic and the NUE bars have more or less a forward peak distribution. And then we can use this kind of a linear stability analysis to calculate in which part of the parameter space do you actually have these fast conversions. So let's take one of these examples. So if you take the emission in this form, where theta is the angle that the neutrinos form with the normal to the emission surface, in such a plane, you can take a simple distribution where the NUEs are isotropic. So there are no backward going neutrinos in the first case. The NUEs are isotropic, so they are flat in a distribution involving cosine of theta. And the NUE bars have a slight anisotropy, which is given by this parameter. So in this parameter, if you linearize the problem and you look for which regions you have a fast oscillation growth, you would see that there are regions where the growth rate can be very large. Similarly, you can also take another model where you consider that the neutrinos are going in the backward direction as well and do a similar analysis. And you would again see that there exist regions where the growth rate is as large as mu, which is proportional to the number density itself. The crux of this study tells you that a necessary condition to obtain fast oscillations in this kind of setups is that you need a zero crossing in this kind of a quantity, which is essentially the difference between the NUE and the NUE bar angular distribution. So what do I mean by this? From a given simulation, you take the NUE angular distribution given by h of theta, which is this guy. You take the NUE bar angular distribution, which is this guy. You take the difference, and this should go through 0 at some point of time. And this is what would give you a condition for the presence of fast instabilities. In other words, or in more physical terms, it demands that in certain regions of the parameter space, you should have more NUE bar as opposed to NUEs in certain directions of the supernova. You can try to corroborate this idea by taking more realistic simulations. You take spectra, neutrino spectra from more realistic simulations, and you see that, let's say in this case, the blue line, which has a zero crossing, will actually have large flavor conversions, whereas the red line, which doesn't have a zero crossing, does not have large flavor conversions. And this kind of confirms this fact. This is still a very active area of study, and people are still trying to understand why is it that this kind of a zero crossing is so important. So this brings me to the second half of the first part of the talk, that this is all a nonlinear numerical phenomena, but can we understand it more analytically? Can we get a more analytical understanding of what is happening? So we can take one of the systems which will be one of the most simple systems that would exhibit this kind of fast oscillations. This is essentially a system of two right-going neutrinos and antineutrinos and two left-going neutrinos and antineutrinos, as I show out here, which are intersecting at some angle theta. And you can label each of these by their individual polarization vectors. What you can show is that you can solve this system numerically, and you can see that this kind of system also undergoes these kind of fast collective oscillations. But why is this special? It's special because this simple system can actually be solved analytically, even with the entire nonlinear equations. So you don't even need to linearize the system. How do you do that? You construct a variable, which is this guy, which is essentially the sum of all these polarization vectors, offset by a tiny value, which is essentially proportional to the mass square differences, mixing angle, and so on. If you start with a system which are all electron neutrinos, this kind of the z component of this vector has an initial value which is essentially 4 minus some tiny quantity. So it's slightly offset from 4. So if you try to solve this problem, you find something very interesting. This entire problem can be analytically mapped onto a classical problem. It's essentially the problem of a particle which is oscillating in a quartic potential, where the potential is essentially given by this. So how does that help us? Firstly, it tells us that these fast oscillations can actually be thought of as a particle which is oscillating in a quartic potential well. Secondly, this kind of a simple model has a lot of predictive power. So for example, if you plot this potential and you look at the evolution of this Q guy, you see that to begin with, Q is some tiny quantity which is less than 4. So if your cosine theta, which is labeled by C out here, is greater than 4, this particle is in a potential where it's in an unstable position. So any tiny perturbation from 4 would allow it to oscillate in this well. However, if you go to a scenario where C is less than 0, then it faces a barrier and it cannot oscillate. You can corroborate this fact by looking at a linear behavior. And as you can see out here, only if C is greater than 0, you start seeing these large growth rates. Otherwise, you do not. Furthermore, since you can simplify this entire problem into that of a classical mechanics problem, you can actually get a very nice analytical handle on the different time scales which are associated with these oscillations. You can use all your standard tools of classical mechanics to calculate these time scales. And then you can try to see how well they match with the numerics. So if you look at this plot out here, the dashed and the solid lines essentially tell you the predictions that you get from your analytical calculations. And if you map them onto these dotted points, these are the ones that you get from your numerics. And you see that there is a very nice match between your numerics and your analytical calculations once you use this kind of a simple model. So this concludes the first half.
5 minutes, okay?
Okay, so this concludes the first half of my talk. Essentially, the two take-home messages from this talk was that in the first work, what we did was we studied fast conversions in very realistic systems, numerically as well as using a stability analysis. And we demonstrated that a necessary condition for the onset of these fast instability is a zero crossing in the neutrino flavor dependent angular spectra. In the second work, we demonstrated that the problem of fast conversions can actually be analytically mapped into a particle oscillating in a quartic potential. And then we estimated the different timescales in this problem. So with this, let us go beyond the standard model and try to see what new physics are these kind of situations sensitive to. So as I discussed before, supernovae are extremely good laboratories to test non-standard neutrino self-interactions, because these are probably the only laboratory on Earth where self-interactions of neutrinos are relevant. So one can try to consider a 4 Fermi interaction of this form, which is essentially a V minus A interaction, excepting that now instead of the weak Fermi coupling, you have a deviation from the Fermi coupling, which is given by this coupling matrix, where each of these small g's essentially encode the deviations. What this does is it changes the Hamiltonian to this form, where these red terms are the new terms that you get. So instead of rho, what you get is you get this thing multiplied by the coupling matrices on either sides. Now, the typical constraints on these neutrino self-interactions are not very strong, and you are allowed to have a coupling as large as 0.01 times the Fermi coupling. What this does is once you put in these kind of self-interactions, you see that many of the well-known results within the standard model change once you invoke these kind of non-standard interactions. Without going into too much details, let me come to some of the major results that you get. So essentially within the standard model, the collective oscillations that I have been talking about, they operate as pair processes. So if you have a nu e going to a nu mu, you would also have a nu e bar going to a nu mu bar. However, if you look at these off-diagonal couplings, they do not respect this kind of scenario. So although within standard model, collective oscillation tries to preserve this net lepton number, this off-diagonal coupling leads to violation of the net flavor lepton number. And this can give you very smoking gun signatures in the supernova spectra. For this, let us focus on the first 20 or 30 milliseconds of the supernova spectra, which is known as the neutronization burst phase. This phase is interesting because within the standard model, this phase does not have collective oscillations, simply because this phase has a very large nu-e flux as compared to nu-e bar. So you do not have enough nu-e bars to cause these kind of pair processes. But now if you introduce these tiny flavor violating couplings, you can actually produce more nu-x's, and then you can cause collective oscillations in the neutronization spectra. What this does is it produces very nice looking spectral splits in your neutronization spectra. What do I mean by this? So within the standard model, what an upcoming neutrino experiment like DUNE would see for the neutronization spectra is given by these red dashed lines. So for the normal mass ordering, it would see something that looks like this. For the inverted mass ordering, this is the neutrino spectra that DUNE would be sensitive to. However, if you introduce very tiny amount of non-standard couplings, you would see these distinct splits. And these distinct splits can actually help you to put flux dependent constraints on these parameters. And because this entire problem is amplified due to its nonlinear effects, it's actually sensitive to very, very tiny values of these couplings. Finally, in the last slide, what we tried to do was we tried to combine everything that we understood before. We tried to combine fast oscillations, we tried to combine non-standard interactions, and we wanted to see how this entire system looks like. What seemed to be intuitive was that because these are very rapid oscillations, you would expect that these rapid oscillations would kind of modulate your standard oscillating signal, and this is exactly what we get. So what we plot in all these 4 plots is again the logarithm of the off-diagonal. It again gives you some understanding of the flavor conversion in the system. And as you can see in this case, which is the standard model case, you have slower bipolar collective oscillations, which are modulated by very rapid fast conversions in a longer time scale. Now, once you switch on these new interactions, the signal changes drastically. So for example, if you have a flavor violating coupling where the GEX is non-zero, you see that the rate of these interactions increases. Whereas if you have a flavor conserving coupling, these oscillations start getting more and more suppressed. And you can look at different kinds of interplays of this. Essentially, what you see is that in a long-term behavior, these fast oscillations are essentially modulated by slower collective oscillations. So the take-home messages from these kind of works was that it showed that supernovae are extremely lucrative sites to test non-standard neutrino self-interactions. In fact, many of these well-known results change, and then this can help us put very strong bounds on non-standard neutrino interactions. Furthermore, if you look at a long-term neutrino spectra, you would expect that all these things to come into play, and you would expect to see a more modulated signal in the final spectra, where all these factors would play an important role. This brings me to my conclusion, where I would conclude with a parting thought as to why these self-induced oscillations are so important. Essentially, these rapid flavor conversions occur deep inside the supernova, and they are not suppressed by tiny mixing angles. So these require the mixing angles only to be tiny seeds, and they can happen for very tiny mixing angles. What this does is it provides you a method of converting the non-electron flavored neutrinos to electron flavored neutrinos deep inside the star. This is important because it's the electron flavored neutrinos that majorly undergo charge current interactions inside the star. So this can change the entire dynamics of the supernova. It can be crucial for reheating the shock wave to cause a successful explosion. It can be crucial to change the neutron to proton ratio inside the star because the nu-e's and the nu-e bars undergo charge current interactions. So in a nutshell, it's absolutely crucial to have a good understanding of neutrino flavor propagation inside a supernova if you want to understand the dynamics of the supernova itself. Thank you.
Fantastic. Thank you very much for a very nice talk, very explanatory, and also which fitted precisely in 20 minutes. So thank you very much again, and congratulations again. So could you stop sharing your screen so I can invite the next speaker? The next speaker is Rafiqul Rahman, who the thesis received an honorable mention, and he talked about study of anomalous gauge boson self-couplings and the role of spin-1 polarization. So Rafiqul,
Yes.
can you begin sharing have you begun sharing your slides? Okay. So again, 20 minutes, and I will give you a warning after 15.
Okay. So am I audible?
Yes, you are audible.
Hello.
You are audible.
Okay.
You are audible, Rafiqul. Can you hear me?
You can see my screen?
We
Yes,
can
I
see
can.
your slides and we can hear you. So please go
Okay.
on. Okay.
Okay. So first of all, I am deeply honored to receive honorable mention for the Rahul Basu Memorial Thesis Award, and also thank you for inviting me for a talk. So I'll be talking on my thesis, which is on study of anomalous gas boson self-coupling and the role of spin-on polarization. So this will be my outline. First, I will give introduction with the motivation. Then I'll talk about the gas boson self-couplings, and I'll talk about some observable which are spin polarization related, which will be used to prove those anomalous coupling. So as we know, standard model is a very successful theory which describes the governing principle of the elementary constituents and their interactions. So however, the SM is not complete. So it has some issues within the theoretical framework such as hierarchy of mass, strong safety problem, and it is also unable to some experimental evidences such as neutrino oscillation, dark matter, and baryogenesis, and etc. So new physics has been postulated to cure those things by predicting new particles and symmetries. Sadly, till today, up to the current reach of energy, we did not found any new physics. So in this case, we can say that the new physics is staying at very high energy scale, not to be directly probed by the current energy reach. So in that case, they will leave footprints in the available energy to us. So they will modify the structure of the standard model interactions or bring some new interactions into the theory. So this kind of effect can be modeled by effective field theory through higher dimensional operators. So the effective higher dimension operators like dimension 6 or dimension 8 uh, can be added to the standard model and then can be proved through various processes in colliders. So first I will talk about the which are the self-gas boson couplings are anomalous. So the Sc2 cross E1 gas boson symmetry allows these WWV couplings in the standard model, but does not allow this VBZ couplings. So the VBZ coupling, which are ZZ, triple Z, ZZ gamma, and Z gamma gamma, are not present in the standard model, but they can appear through some higher dimensional effect. So in the operator language within the Sc2 cross E1 gas symmetry, so these are the 5 set of operators at dimension 6 at the lowest contributes to the WWV anomalous couplings. So out of which these triple tilde observables are the CP violating ones, CP odd ones, and these until the 3 are CP even ones. So likely for the ZVB couplings, so the high dimensional operator arrives at dimension 8 only, and there are 4 dimension 8 operators. So out of these 3 are CP odd operators, and this one is CP even operators. So this we can also actually construct some Lagrangian out of those anomalous couplings by within the Lorentz invariant framework, uh, not always respecting the Sc2 cross E1 gas invariance. Okay, I'll talk about this later when I come to some process in collider physics. So so these operators have some contribution, some known theory, as I said earlier. So for example, two Higgs doublet model can contribute to this charge triple gas boson coupling as well as this neutral triple gas boson coupling through the Higgs and the these Goldstone moods appearing in the loop of a triangular diagram. So let's talk about the polarization observables. So as we know, the spin half production density matrix of a spin half particle can be written as a 2 by 2 matrix plus vector polarization P. That sigma is the spin matrices in the spin half cases. So likewise, for spin 1 particle, we'll have a vector polarization P as well as a tensor polarization component Tij. So upon expanding this, we get the known form of the spin up particle. And for the spin 1 case, we have uh, this these matrices. So this is called the polarization density matrix. So if we can calculate the production density matrix and normalized it to, and comparing with this equation, we can calculate these parameters P and T. So P's are the vector polarization of the particle and T are the tensor polarization of the particle. So T's are this density, this tensor Tij is a traceless symmetric tensor. So it has a 5 independent component, and we have 3 vector polarizations. So we total have 8 polarization component that you can use. So in the detector, so we have to use the decay of the spinful particle. So if we consider the decay of a spin 1 particle and uh, use combined it with the production density matrix, so we have this nice decay distribution of the decay fermion. So this fermion contains the polarization information of its mother particle. So we can use this formula to generate some asymmetries, to construct some asymmetries, so that can be used to get the polarization information in a detector or in a Monte Carlo processes. So for example, if you want to extract the polarization parameter Px, so we have to construct an asymmetry like this. We integrate our whole range of theta, then integrate of the left side of the phi region, that is minus pi by 2 plus pi by 2. Then on the other side, that is pi by 2 to 3 pi by 2, then subtract. So we'll obtain this 3 alpha p by 4. So this alpha is related to some is the decay density matrix, so which is called the analyzing power, which actually okay, it depends on the decayed particle, which I mean how the mother particle is decaying. So in other words, so this formula can be presented like this: this cos phi greater than 0 and sin cos phi less than 0. If we construct an asymmetry in these two regions, so we'll obtain this value. So so this is a visual for a visual purpose. So this left sides and the right sides take integration in the both side and subtract and divide with the total. So we'll have the asymmetry. So likewise, all the asymmetries can be constructed and to probe all the polarization parameter like this. So here to mention that this AY, which is related to sin phi, and AXY, which is related to sin 2 phi, and AYZ, which is related to cos theta and sin phi, are actually CP odd observable. So which can probe CP odd couplings. So for example, these polarization observables have many effects like constraining. It can help constraining the anomalous coupling on top of the cross section, and also it can distinguish between CP even and CP odd couplings. So for example, consider this process of ZZ and Z gamma production at an EP collider. So we have this, as I said earlier, that other than the SU2 cross E1 gauge invariance method, we can also have a general form factors which are just Lorentz invariance and E1 boson E1 symmetry. So this F and H are the anomalous coupling, where F appears only in the ZZ production process and H appears in the Z gamma final state production process. So out of them, this red colored F4 and this H1 are the CP odd couplings and others are CP even. So if you see the sensitivity, for example, in the one jet going to electronically and another jet decaying to hardonically at 500 GeV root S and 100 femto1 inverse luminosity ILC. So we see that this is a F5 jet, which is a CP even coupling, and F4 jet, which is a CP odd coupling. So together with the cross section, we give the sensitivity of all the observables here, all the polarization observables, which are non-zero. So only these are actually non-zero. This contribute here. So we see apart from the sigma x, x square, y square, and azz. So ay in blue dashed and xy in red dotted are not present in this F5Z, which are actually flat. But in F4Z, which is CP odd couplings, we see that this CP odd observable AY in blue dashed and AXY in red dotted appears here. So we can see that certainly it distinguishes between the CP odd and CP even couplings nicely. So as I said, it can also help in constraining that anomalous coupling. So for example, we see the WW production process in E plus E minus collider. So where this set of form factors can appear in these processes. So which are okay. And here also G4V, lambda gamma, lambda V tilde and kappa V tilde are CP odd and others are CP even. So V is for Z or gamma. So that means this actually this S channel propagator V is responsible for this V. So if you see in some I mean representative diagram, lambda gamma and lambda Z plane. So this we see that if we just use the cross section, we have this nearly circular region, which is allowed at 95% confidence limit. And for the just for the polarization, we see a correlated this dashed blue region, sorry, line. And if you combine with the cross section, we see that the region shrink, and also it also have a little bit less correlated. So clearly that polarization, all the observables, helps to constrain those couplings on top of the cross section. So on top of that, if we use the beam polarization, so
Rafiqul, we cannot hear you. Rafiqul. Hello.
Yeah, Renu, I think he's disconnected. So.
Oh, okay. That's what I wanted to check. I thought whether it was my connection.
No.
So what do we do?
Maybe we can wait for 30 seconds and then we move to the next topic. Yeah.
Because I thought for a minute that it was my connection.
Yeah, now he's disconnected. So
okay.
Yeah.
hello.
Hello, Rafiqul. You were
Yes, am I
disconnected.
audible?
So please continue. Yeah,
Okay.
you are audible. Your slides are not being seen yet. So are you having connection problems? Because maybe then we have to move to the next speaker if this continues. Are you able to share the slides? Or Bedanga, can you project his slides?
Okay, I will do, ma'am.
Yeah.
So
Yeah, so Rafiqul, your slides will be projected from Vedanga's end, and I hope you can see them. And which slide were you on? Will you please remind us? Go much further, I'm sure. Vedanga? Further, I know that. Beyond this, this was done. This was over. This was over. This was done. I think this is where he was, perhaps. So Rafiqul, is that the right slide?
I think he's disconnected again, so we should move to the next.
I think we'll have to move to the next talk then, because.
okay. So should I stop sharing?
Yeah, I guess so, because we don't have him.
Okay.
If you have his number, you can just call him separately and tell him. It's a pity, but I think in interest of time, we have to move forward. So, Rashmi, are you ready?
Hello.
Hello, Rashmi. If you're ready, please start sharing your screen.
Yes,
And,
am I audible?
Yeah, you're audible. So I'm now inviting Rashmi, who is the second award winner of this year. And again, Rashmi, the same thing, 20 minutes, and I will give you a warning after 50.
Okay.
Okay.
Yeah, okay, thank you, ma'am.
Please go
are
ahead.
my slides visible in full screen?
The slides are visible. We can hear you. They are in full screen. You can start.
Okay. First of all, I would like to thank the award committee for choosing me as one of the awardee. I'm extremely delighted and honored for this and also for the opportunity to talk about my thesis here. So the title of my thesis is a measurement of the CKM angle phi3 from B to DK, D to K short pi 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 0 decays and future prospects. So this is supervised by Professor Jim Libby at IIT Madras. So in this talk, I'll give a brief introduction into the topic, followed by the measurements that was done in CLIO-C data and Bell data to measure the parameter phi3 with the inputs, strong phase inputs from CLIO-C. And in the end, prospects at Bell 2, which was at the end of its commissioning stage while during the time of my PhD and successfully taking data now. So first a brief deviation into my current involvements. So as we know, the standard model is the lepton flavor universal, which means that the electroweak couplings to all the charged leptons are universal. The difference between them is only driven by their masses. And this can be tested, for example, in B2C transitions by looking at the ratios of branching fractions of B2C tau nu to that of B2C L nu. And interestingly, all the measurements of this kind so far have been away from the standard model prediction. So if in particular, the combination of RD and RD star is about 3.8 sigma above the standard model and the parameter RGEP psi being 2 sigma above the standard model. So currently I'm working on the RD star measurement at LHCb. So looking at the evidence, looking for the evidence of anomalies at these tree level processes are complementary to what I've been doing during my PhD. That is testing the standard model description at tree level with the CKM angle phi3. So this is the only CKM angle accessible at tree level decays. The measured value of phi3 has a large uncertainty, as can be seen on the top left figure here with this large band of uncertainty. And this uncertainty is also more than twice as that of the predicted value of phi3, the uncertainty on the predicted value, which is inferred from all the other constraints and assuming the closure of the triangle. So comparing these two phi3 values would allow us to compare the constraints coming from tree level as well as loop level quantities. But as can be seen in these last bottom two figures, the uncertainty on the apex of the triangle is larger in the case of constraints from tree level processes, which is mainly due to this large uncertainty on the value of phi3, the measured value of phi3. So in order to have a fair comparison and look for any new physics effects possible in loop level processes, the uncertainty on the measured value of phi3 needs to be reduced much further. And more measurements with different decay modes are needed to bring down the uncertainty on this average value of phi3 measured. The angle is accessible due to the interference between B2D0K and B2D0 bar K decays. And as I mentioned earlier, these are tree level diagrams, and in the absence of any penguin contributions, the theoretical uncertainties are very small, of the order of 10 power minus 7. The Feynman diagrams of these two processes are shown here. So one is a color allowed process and the other a color suppressed one, and their amplitudes can be written as shown here, and phi3 comes as a weak phase here, and RB is the ratio of the magnitude of these amplitudes, and delta B is the strong phase. However, the phi3 measurement is statistically limited due to the small branching fractions of these decays involved, and this statistical uncertainty is inversely proportional to the value RB. So to compare, the RB value for B2DK is about 0.1, whereas for B2D pi, which are similar decays, the values much smaller, and hence they are not sensitive to phi3. However, they serve as excellent calibration modes due to the similar topology as well as a larger sample size. So for a self-conjugate multibody final state, Bind-Dalitz plot formalism is used to extract phi3. So this can be done in states like K-short pi pi, K-short KK, or K-short pi 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 0. So a model of an example of the Dalitz plot is shown on the left here for the D2 K-short pi pi mode, which is divided into different regions called bins. And in each of these bins, the decay rate for B minus decay and B plus decay could be expressed as in this equation here, where the parameters x and y are formed, Cartesian coordinates formed from RB, delta B, and phi3. So these are our parameters of interest here with inputs that are Ci and Si, which are cosine and sine of the strong phase difference between D0 and D0 bar averaged over in each bin. And they are taken as input from a charm factory like CLIOC or BES3. Ki and Ki bar are the fraction of flavor tagged D events, which are obtained from D star to D pi decays. So in our case, at Bell itself. And in this right hand side plot, the B plus and B minus yields for D2 K-short pi pi are shown from the analysis in Bell data. So in some bins, clear deviation of between B plus and B minus yield can be seen, and this is the evidence of direct CP violation. So the dominant mode in this model independent measurement of phi3 is D2 K-short pi pi. But the decay D2 K-short pi 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 0 has also a large branching fraction of 5.2%, and the D star to D pi decays with D2 K-short pi 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 0 had given a larger set of events in Bell data set. The decay proceeds through some interesting resonant substructures like K-short omega, which is a CP eigenstate, and a Kabibov favored state like K star pi pi 0, etc. But binding a 5-dimensional phase space is non-trivial and challenging. So I'll now move on to first the measurement of the strong phase parameters at the CLEO-C. So the CLEO-C data corresponds to 0.8 femtobarn inverse, and the psi 377 resonance decays into a pair of D mesons which are produced coherently in a C equal to -1 state. The good 4 pi solid angle coverage of a CLEO-C detector allows for a full reconstruction of the D-bar event. A schematic of the detector is shown here on the left hand side. So the right hand side cartoon shows a typical event at CLEO-C with psi 3770 decaying into a D0 and D0 bar, and one of the meson is reconstructed in the signal mode of interest, that is K short pi plus pi minus pi 0, and the other D into different modes which we call tags. And the decay rate depends on the CP eigenvalue of these D final states. So there is a twofold enhancement if they are of opposite CP, and 0 if they are of the same CP. So depending on the decay rates with different tag modes, there is a sensitivity to the parameters Ci and Si. So here I being a bin in the D phase space. So this phase binning scheme is chosen around the different resonances that are present in the decay. So we have 9 bin scheme that is then exclusively. So the different bins chosen are given in this table, and an example of the first bin that is chosen around the omega resonance is shown in this top right figure. The Ci and Si parameter results from these 9 bins along with their uncertainties are shown in this bottom figure here, and these numbers are used as inputs in our analysis to extract phi 3 from Bell. So KKB is an asymmetric E plus E minus collider with a 8 GeV electron and 3.5 GeV positron. The schematic is shown on the left, and its interaction point sits the Bell detector, which has this structure as shown on the right hand side plot, and it comprises of tracking systems, particle identification detectors, and electromagnetic calorimeter, and these are crucial for the analysis that is presented here. So at Bell, there is a 772 million BB bar pairs produced at epsilon 4s resonance, and this corresponds to 711 femtobarn inverse of data collected during 1999 to 2010, a span of about 10 years. So the events of B to DK and B to D pi with the D going to K short pi 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 0 are selected in a similar way with the track quality criteria. K-on pi-on separation using the PID information from the detectors, then invariant masses of unstable particles that are D, K short and pi 0 within 3 sigma of their PDG masses. Then we define 2 variables MDC and delta E from the beam energy and the form momentum variables, and the distributions are shown here along with the selected regions for these variables, and the delta E is one of the variables that we use in the fit to extract the signal yield in the end. So the main background is coming from E plus E minus 2 QQ bar events where Q is a lighter quark, U, D, S or C. So if we compare them to BB bar events as shown in this schematic here, so for epsilon 4s to BB bar, the available energy is just above the threshold of producing a BB bar pair. So there is these are the BB bar pairs are produced almost at rest in the epsilon 4s center of mass frame, and as they are scalars, there is no preferred direction, and hence the event forms a uniform spherical topology. But in the case of lighter quarks, they are produced with large initial momentum, resulting in a jet-like topology, And the difference in this event shape is utilized in a neural network to separate the continuum background, as we call them, from the signal-like events. So the output of the neural network is shown on the left-hand side here. And this can be transformed into a form as shown on the right, which is easier to model analytically. And this is this CNN prime variable is the second variable in the signal extraction procedure along with delta E, as just mentioned in the previous slide. So here, this is just to illustrate the effect of this suppression of the continuum background. So on the left-hand side, the delta E distribution without any criteria on this continuum background suppression, and on the right-hand side is after applying this cut on the neural network output. So here, these yellow and cyan are the events coming from the lighter quarks U, D, S, and C, and red is the signal. So here the signal is barely visible in this sea of continuum background. But after this continuum suppression algorithm applied, this U, D, S, and C background has significantly reduced, and the signal is clearly visible. And this will be more crucial at Bell2 with a large statistics sample. So the signal extraction is done from an extended maximum likelihood fit to the variables delta E and CNN prime simultaneously to the signal mode B2DK and the control sample mode B2D-pi. So the fit projections for these two are shown in the slide here with the components signal, continuum background, other B backgrounds, and also K-on-Pi-on crossfeed background due to the misidentification between these two. So this is predominantly seen in the case of B2DK because B2D-pi has a larger branching fraction. And they are shifted by 50 MeV in delta E due to the wrong mass hypothesis used for the reconstruction. And the fit model was tested with the 0 experiments as well as some Monte Carlo samples to test for any bias. In the end, we obtained about
5 more minutes.
Yeah, sure. Thank you, ma'am. 815 signal events for B2DK and around 10,000 events for B2D-pi. And we extract the parameters X and Y with the inputs CI and SI that are measured in the CLIO-C data, and KI and KI bar that are measured in the D star to D-pi data at Bell. The results of X and Y are shown in this table here, where the first uncertainty is statistical, second is systematic, and the third one is due to this external inputs of CI and SI. And the 1, 2, and 3 sigma contours for these XY parameters are shown on the right separately for B2DK, sorry, B plus 2DK plus and B minus 2DK minus. And in the end, we obtain the physical parameters phi3, RB, and delta B from these measured XY values using a frequentist treatment with the Feldman-Cousins ordering. And the results along with the 2 sigma interval are shown in this table here. And the 1, 2, and 3 sigma contours of delta B, RB, and delta B, sorry, phi3 RB and phi3 delta B planes are shown on the bottom. And we include the current world average values at the 2 sigma level as shown in with this plus sign. And from all the model independent analysis at Bell, the value of phi3 is obtained about 74 plus 13 minus 14 degree. So this is including this result. As can be seen, this measurement is statistically limited, and the prospect is more with the larger data. And in this direction, Bell 2 is which is a significant improvement, upgrade of the Bell experiment. So I'll just briefly show the work that we did on Bell 2. So Bell 2 aims to collect 50 times more data. And in particular, the new vertex system, the vertex detector has 2 layers of pixel and 4 layers of strip detectors. And The fourth layer of this vertex detector was exclusively built by India, mainly by TIFR. So I've been part of the construction and quality assurance of this with the scientific team from TIFR. The assembled ladders and the sensors have been tested for geometrical tolerance as well as electrical response, and a sample of the results from these tests are shown on this right hand side of the slide here. And the first data from BEL2 came during April to July 2018, which comprises about 0.5 femtobarn inverse, and this is 1 by 100,000 of the total expected data. And in this small sample, we had around 245 B candidates, which are reconstructed from hadronic final states as shown in this MBC distribution here. So I had led the effort to rediscover the first B mesons at BEL2 in these different modes shown here. And these are all modes which are useful to extract the CKM parameters. And with the ongoing data taking, this shows good physics prospects. So in summary, I've shown that the mode D2K short pi 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 0 is a promising candidate to measure the CKM angle phi 3, which is important test of a standard model description of a CP violation. So first, the strong phase difference parameters were measured at CLIOC, followed by a measurement of phi 3 at BEL for the first time with this decay mode D2DK, D2K short pi 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 0. And with a larger data set at BEL2, we expect an uncertainty of around 4.4 degree from this single mode alone. And I've also been part of the vertex detector construction at BEL2, as well as the analysis of data taken during the pilot run of BEL2. Thank you.
Thank you very much, Resmi, again for finishing good in time and giving us an overview of your work. So thanks again and congratulations again. So can you stop sharing your screen now? So Bidanga, should we have Rafiqul stock now or Suman stock now? You tell us.
He is ready.
He is ready. So then we go on with Rafiqul stock, continue where he had left. And then Suman, you be ready. We will take you later.
Yeah, sure.
Just 1 minute, Rohini.
Yes, ma'am.
I want to say congratulations to Reshmi.
Yes, please do.
Yeah. So congratulations, Reshmi. I'm really proud of you. Thank you.
Thank you, ma'am. That means a lot to me.
Okay, so should I share my screen or?
Yes, I don't know. Depends on your internet. You decide with Vedanga. I don't want to get into
it. I think we can share.
We can project your slide. Why don't we do it, Ranbir, please?
They will project. Yes. I think that would be better.
Yes. So
go ahead.
So I was stuck here, maybe.
Yes, right. Yeah.
Yes. So so we are trying to use the polarization observable to probe the anomalous coupling. So to see how good they are apart from the cross section. So earlier I showed that this polarization observable are good for distinguishing between CP even and CP odd coupling. So now this one in the WW production, so I wanted to say that these polarization observable are helpful in constraining the anomalous coupling as well. So in this process, this WW production process, this vertex, this blob in the second diagram, in the second Feynman diagram, represents the anomalous contribution on top of the SM. So so this G4V and lambda V tilde and kappa V tilde in the Lagrangian LWWV, the CP odd couplings here, and others are CP even. So there are total 14. And some of them are not invariant under SU2 cross E1 invariant, like delta G1 gamma, G4V, and G5V. So they are 0 if we consider the SU2 cross E1 gauge invariance. So in that case, we can actually equate these form factors with the operators earlier issue. Okay, next slide, please. So in this two-dimensional projection of lambda gamma lambda z plane, so we see that in here we use 1W decaying hadronically and W minus decaying leptonically. So we use the lepton distribution to construct the W minus polarization. So we use only W minus polarization here, not the W plus. So we use this because to reconstruct the neutrino longitudinal momenta. In this case, it is possible in the A plus minus collider. While if both are leptonically decaying, so it will not be possible to reconstruct both the neutrinos. So if you use just the cross section, as you can see, we get the black dotted contours, the larger contours, which is roughly circular. And if we just use the polarization observable, which is denoted by dashed blue contours, which has some correlation with lambda gamma and lambda z. And also it is visible that it is the polarization alone itself can constrain better than the cross section. And if we combine with the cross section, so of course we will have better limits on the lambda gamma and lambda z. So next slide, please. On top of the polarization observable, if we use the beam polarization of the electron and positron, so we'll have much better results. I mean, much better limits on the couplings. For example, in the same lambda gamma and lambda z plane, so the right sides are the beam polarization points, where the left ones are the beam polarization for electron and the right ones are for the positron. And we use the electron and beam polarization oppositely, equal and opposite, and the two sets can be possible with electron beam polarization, for example, minus 0.2 and positron to be plus 0.2. And the opposite one, that is electron to be plus 0.2 and beam positron to be minus 0.2. And both the set has to be used because the collider is supposed to be run like this to avoid some what you can say, the systematic error coming from the luminosity. So in this case, as you can see, if we increase the modulus of the strength of the beam polarization, we see that the contours actually the correlation dies away and the contours get shrink around the unpolarized around the standard model point. So this, as you can see, the dashed big dashed with the black color is for the unpolarized case, and for the experimentally available best beam polarization, which is plus minus 0.8 for the electron and plus minus 0.6 for the positron, which is denoted by the green contour. So that will be the best limit what you can achieve with the beam polarization. Okay, so next slide, please. So how do okay, at the LIC, as the polarization asymmetries actually do well in the E plus E minus collider, but they are not they do not well in the LHC. So like they are capable of constraining the anomalous coupling at ILC.
We could have about 3 more minutes, okay? 3 to 4 minutes.
Okay. Yes, this probably is the last one. So at the LHC, so the cross section dominates over the polarization observables. So, but in the left plot, as you can see, if we just use all the asymmetry, so here we use both the W polarization. We combine the two processes here because both the process will contribute the same anomalous coupling. And we use the Z polarization and W polarization and W plus minus polarization both. So here we have this. We reconstructed the longitudinal neutrino momenta with the W boson mass. We will have a two solution. Out of that, we choose one of the solution with which has the smallest magnitude longitudinal momenta. So that actually satisfies the correct one up to 65% times. So that is the best thing we can achieve till now. So from the left plot, as you can see, if you use just all the asymmetry here, so we have a larger contour than the cross section itself, and if we use all the asymmetry with the cross section, so we see the solid green line. So as you can see, the only with the asymmetry we may have some directionality in the anomalous coupling plane, but when we combine with the cross section, the directionality dies away. But that is around the standard model point. If we have some non-standard model point, a non-zero value of the anomalous coupling, we can see that this anomalous polarization observable actually helps in extracting those coupling, non-zero coupling. As you can see in the right plot, in the delta kappa z and kappa z tilde plane. So if you use this non-zero value of the anomalous coupling marked with a star on the plot itself, and the values are given below. So as you can see, if you use the cross section, we just have this dotted red contours, which actually combines both the standard model and the non-standard model point as well. So with just the cross section, we will not be able to see where this non-zero value lies. But if you use the anomalous coupling, polarization asymmetry, for example, if we just use a delta phi, this delta phi asymmetry of the Z and of the electron coming from the W. So we can see this, that actually distinguishes between two regions, where one of the region contains this non-standard point. And if we use all the asymmetries together with the cross section, you can see that this contour actually just contains this region and does not contain the opposite region. So this polarization asymmetries along with another asymmetry a delta phi actually helps to extract some non-zero value if available, or if possible found in the collider. So next slide, please. So to conclude that these polarization observables are helpful in many ways, like it can distinguish between CP even and CP odd couplings. So it also can help this constrain the anomalous coupling. So upon that, if we use the beam polarization, the limits can be improved much more. And at the LAC, even though they do not give any directionality, they do not help in constraining the anomalous coupling, they actually help in extracting the values of non-zero coupling if observed at the LAC. So on top of the this polarization observable, one can have spin-spin correlation asymmetry as well, which if we use, the limit can be improved further. So thank you. I'm sorry for the earlier disruption in the due to the internet connectivity.
Okay, so thank you, Rafiku, and again, congratulations on your achievement and good luck in your future. So now I invite the last speaker in the session, and that is Suman. So Suman, can you please start sharing your slides?
Yeah,
and
I'm sharing now.
Yeah, and please start, and you have 20 minutes, and I will inform you after 15, and please remain within time, like all the others.
Yeah.
Thank you again, and congratulations again.
Thank you, ma'am. So, first of all, it's an absolute honor for me to give a talk in the memory of Rahul Basu. So, first I thank all the members of the committee who chose the thesis for the honorable mention. And here is the first page of my thesis, where I try to summarize most of my work I did in my PhD under the guidance of Professor Govinda Majumdar. And here is also a link to my thesis. In this talk, I'll try to cover 3 topics. The first 2 I did in CMS collaboration. The third one is a FENO work, which I did with Rohini and Tuhin. And so, as you see that in my title of, in the title of my talk, and that is jets with a central character. So what are they? So just try to map what you compute in the theory to what you measure in the experiment. So for example, you can just compute the cross-section for the quark-antiquark pair production in electron-positron annihilation, and then but you can't observe the free quarks in the experiment. So the quark radiate gluons radiate quark-antiquark pairs, and this pattern shaft goes on till the Fermi scale, where the strain between the quarks and gluons are so strong that they form the colorless hadrons, and these hadrons are the ones which come to our detector and appear as charged tracks or the energy deposit in the calorimeter. And from these charged tracks and the calorimeter clusters, we, on top of this signals of photometer in the detector, we apply some algorithm which, as outputs, give us the jets. So jets that's the output of some algorithm, and the algorithm is constructed in such a way that the jet can act as proxy of the initial quarks of the gluons. So there are two possible origins of the jets at, for example, LHC. One is the normal quark-quark or quark-gluon or gluon-gluon scattering. So they scatter and produce new quarks or gluons, which gives rise to jets. You can also have the formation of the colorless particles. For example, a new particle which is labeled as X in the right figure, which can decay to a pair of top quarks, and top quark decays immediately, and then we have the quarks which gives rise to your jets. And I have also a Z boson which decays to a pair of quarks. So at LHC, we use the antiquity algorithm to reconstruct jets, which gives us nice circular jets. So it starts from a high PT particle and then clusters the soft particles surrounding it. So it starts from a hard core, then expands. And there are details about the algorithms in the talk by Ogun in some mini review talk in the symposium. And one thing is that in the algorithm, there is one parameter which the user puts as an input, which is called the distance parameter. For anti-gravity jets, it just gives you the scale of the radius of the jets because you have circular jets. So, and in the first topic of my talk, I'll just show that how important is this parameter as far as different processes are concerned in the jet formation. So in slide 7, so first we have the hard scattering, which with quarks and gluons. So now, so in theory, you can have a jet from the quarks and gluons, but then when the different processes happen, so there are different mechanisms of the energy loss from the parton to jet. So first, when the quark radiates the gluons and you put a cone of fixed size around the hard quark, you miss some amount of parton radiation. And naively, we expect that the smaller the cone size is, the larger your loss is. And if you compute it in QCD with some approximation, you see that log R dependence. And in hadronization, there is also a loss of energy from parton to jet. And it goes roughly as inverse of the jet size. And then in the hadron collider, you have also underlying event from the multiple parton interaction from the colliding photons, and also beam wavelengths, which throw soft particle in your jet cone. And as you naively expect, the larger the jet size is, the other the pollution for underlying event is there. So you try to model all these processes in a simulation. So there are two kinds of programs, the Monte Carlo programs. So one kind is the all-purpose event generators, which try to simulate all the different stages in the jet formation, like PTR, Havik, or Sherpa. And they use different schemes for parton sharding, hadronization, and underlying event. There are also some generators which just generate the hard interaction, like MADGRAPH, which does it at leading order in QCD, or PAVEC, which does it approximately at next leading order in perturbative QCD. And then you use the PTR Havik for the remaining states. You can also compute the cross section of the hard interaction in terms of some variables using programs like at fixed order in QCD using some programs like IntelliJ++. So you see that different processes are different in nature, affecting the choice of jet size. So the measurement of jets of different sizes give us an idea of how different processes are modeled in simulation or calculation. So the first measurement is that a ratio of cross section. In the numerator, we have the double differential cross section of anti-KT jets of different sizes. So AK means anti-KT, N is it means the jet size, is 0.1 times N. And in the denominator, we have the same thing for one particular jet size, which is anti-KT jets of 0.4. That's why you have the line for 0.4 at 1. You see that, and here we compare that data, which are the markers, and the prediction from PowerVec, which generates the digest process at next leading order in part of it QCD, are followed by PCI pattern sharing. So for low to medium jet sizes, the prediction and the data are very close. But when you move to very large jet sizes, say 1, 1.2, in the low PT side, you see that your data is consistently above the prediction, which tells that, so as I have seen in the last slide, that in low, for large various sets, underlying events is important, and it's also important in the low PT region. So you need a better modeling of underlying event in PTR for large various sets. That's one lesson we learned from here. In the next slide, so you can compute the cross-section ratios just using a perturbative QCD, just fixture calculation. So we just compute the ratio at leading order in QCD. It is far away from the data, and also when you do a QCD computation, it's with quarks and gluons, but you actually reconstruct jets using hadrons in experiment. So there needs to be a non-perturbative correction for hadronization and underlying event. So if we apply the correction on top of the leading order prediction, the shape comes close to the data, but still is quite away from the data. The base prediction you have only when you have the computation at next leading order in perturbative QCD times the non-perturbative correction, which is the blue line here, and the black dots are the data. You can also have a good prediction with the resummed calculation at next leading log. So thing is that it's important to go for high order QCD calculation, and it's important to use non-perturbative corrections as well. Okay, so in slide 10, so you can also measure the absolute cross sections. So far I've shown the cross section ratios because those are much more precise. But you can just count the number of jets in one PT region for different jet sizes. That's what we do here, and different colors have different predictions. In this figure, there is no data, and just for visualization, we just scale all the points by the Havik 7 prediction, which is the green star at radius 0.4. So this is just a common scaling for all the points. The main thing you see that your PTI and Havik predictions, which are at leading order generators, are at the two edges. When you go to PowerVec, which composes the cross section at NLO, then the PowerVec predictions with PCI or Havik pattern shafts are quite close together. It's also very close with the Havik 7 prediction, which is also next leading order. So there, these different predictions, they are not, so they have some difference, but they have quite similar trend as a function of the jet size. So what you see in the ratio plot in the bottom panel. But if you compute the cross section just using the fixed order QCD at NLO with a non-perturbative correction, especially in the low jet sizes, the shape deviates significantly from the Monte Carlo predictions, and that's because at low jet sizes the pattern branching is very important, which is not really taken care of in the fixed order calculation. Next, when we add the data, here all the points are scaled by the corresponding prediction at r equals to 0.4. So that at r equals to 0.4, all the points, all the predictions are at 1 by construction. So you see that all the Monte Carlo predictions are quite close to the data. So they describe the data really well. And the black open square, which is leading order prediction for the cross-section ratio. So there is one trick here. When you go from absolute cross-section to cross-section ratio, the precision of your perturbative calculation gets reduced. So that's why what we had in LO in the absolute cross-section is approximately at LO in a cross-section ratio, which is far away from the data. You can also compute the cross-section ratio purely at NLO using some tricks, and that brings the prediction much closer to the data. And in the orange lines, which are like hard to see, those are the resum calculation, which are very close to the data. So it is important to use resummation so that you can describe the data really well, and it's also important to go for the high order calculation appropriately. And this kind of measurement of jets of different size So this is the first time at colliders, and there is also a low PT measurement from Alice, which complements our result beautifully. So next, I will go to a search for W prime boson, which decays to a top and a bottom quark, and the W boson from the top quark decays hadronically. Okay, so the W prime is kind of, you can think of a heavy partner of W boson, and you can have it in our models which mainly try to solve the hierarchy problem. And but so we're doing the search in the TB channel. So why is that? So first thing is that you can have a much stronger bound from the mu decay, so you have a high PT electron and missing energy, and at last gives a 6 TB bound on the W prime mass. But thing is that first of all, so there are some theoretical models which predict an enhanced coupling of W prime to the fermions of the third generation, and like there are some LFB models which explain the B anomalies, and also you can construct a model such that you bypass the inu constraint. Like if your model in a model the W prime is leptophobic, so it can't decay into leptons, or if in the right-handed case the neutrino is heavier than the W prime, it can decay into leptons. So then it can decay only into quarks, and in that case, so as compared to the light quark final state like UD or CS, TB is much better because you can use top tagging and tagging techniques to reduce the multi-jet background to a great extent. But it also comes with a challenge that you need to tag the top quarks and the B quarks at high PT, which is not very easy. So here is what you see, or what do you expect to see in the experiment. So the B quark from a heavy W prime gives you a high PT small various jet. So for that we use AK4 jet, so anti-KT 0.4. So you check for a high PT AK4 jet and check if it's a B tagged or not. And when the W prime is heavy, the top quark from the W prime has high transverse momentum, and all the decay products of it are collimated into a large various jet. So you can check if the jet is top tagged or not. So let's say B tagging or top tagging. So this is kind of we make a classifier using deep neural network, so which given a jet tells how likely is the jet B tagged, or is from a B quark or from a top quark. For top tagging, we also use mass, not the normal jet mass, but after some cleaning of the QCD splittings. And then after we have a B tagged AK4 jet and a top tagged AK8 jet, we just check their invariant mass. And what a Shannon model tells you that this should be a continuous falling spectrum. And if there's a W prime, you expect a peak on this falling spectrum. So you hunt for a bump on the falling spectrum. So here is the result for hunting. So first, let's look at the right side plot. So this is in a background enriched region. So your AK8 jet is not top tagged. It fails the top tagging condition, but the AK4 jet is B tagged. And actually, the signals are scaled to appear in the figure. So here there is actually not this much signal. So in this region, you just check the consistency of your background with data, just to check if the background estimation is correct or not. So the green portion, which is the multi-jet QCD background, is taken from data completely. The magenta is from TT bar production, which is taken from simulation, but we then add algebra-based correction on top of that. A single top, the small background is taken from simulation purely. And you see that there is a quite good agreement between prediction and the data. And then we look for the signal region where we have top tagged AK8 jet and B tagged AK4 jet. So here, so this is the region where we, okay, I'll try to be fast. So yeah, so here we expect the maximum signal, but we don't see it. So because there is a good agreement between data and simulation, not simulation, but in the background, except one point at 3 TeV, but it's also very small excess. So we set the limits in one model, and we exclude W prime up to 3.4 TeV. And this is currently the best result in the hadronic final state. So I'll quickly go to the last topic, which is tagging tops, which decay into electrons. So we have seen that there are already interesting scenarios where you can have a boosted top quarks, and if it's boosted, you can use a fat jet to capture all the products of it, so that you don't take into account the combinatorial problem in the top reconstruction. But for the case where the W boson decays to electron, and if the top is boosted, the hadrons from the B quark are close by with the electron, So the electron may not be reconstructed. And also, unlike the hadronic decay, you have a missing piece, neutrino, so that you can really check the mass of the jet. So first thing we do, we start from a fat jet, and we make some subjects in the fat jet and use all the constituents of the jet and the subjects to construct some variables. For example, on the right side, there is one variable which we propose is the asymmetry between the energy of composition of these subjects, and which separates beautifully the electronic tops than the B quark jets, which is the blue, light quark or gluon jets, which is the dark red, and hadronic top jets, which is the green. And there are also some other variables, and then we put them in a BDT so that we map a multidimensional problem into a single dimension where such the BDT response separates your signal, the electronic tops, from all the backgrounds. And here you see that you use only the electronic tops and BJs to train the BDT, but it separates all the standard model backgrounds like light quark or gluon jets or hadronic tops. But if you have a stop which decays to a B quark, electron, neutrino, and neutrino, you have same visible particles in your detector. So that the stop behaves similarly as the top. So how to separate those? For that, we need to use now the neutrino part. So we make some so we use a hypothesis that there is only one missing piece, and that's neutrino. And using this and with some approximation, which I will not go over because I don't have time for that. So we construct some variables which is sensitive to the missing piece. And for that, we use the top and W kinematic constants. And again, we just construct two different variables which reflect the properties of the missing neutrino. And then we again construct a BGT with these two variables, which is not very good, but it does the essential job. It separates the top and the stop jets. And mind you, we don't really use the stop signal in the BGT training. We use the BJet as background. So what does the job? Because the standard model backgrounds look similar to the stop. Now you can construct 2D plane of these two BGT responses. By construction, your electronic tops are on the top right corner, and all the standard model backgrounds are on the left corner. And now you see that 2D PDF of the stop jets in this plane is the stops are in the bottom right corner. And this is the place where you don't expect much contribution from standard model processes like top or the QCD jets. So this is a good place to look for a new physics where you know that you don't have much contribution from standard model. So this can be used in future. So here I'll summarize. So I'll not go through those again. So there are three topics which I have presented. The first one is precision measurement in QCD. Second is the search for new physics. And third one is a tool which can be used both in the measurement and also in a search. And I'll just stop by saying that we are on the track of an exciting adventure, and we will continue doing so in the next future. Thank you.
Thank you very much, Suman, again. And again, congratulations. And can you stop sharing your slides?
Sure, just give me a second. Yeah.
So let me sort of now try to make some concluding remarks in view of the fact that we are already beyond our allotted time. So Bedanga, can I have the few more minutes, 2 or 3 more minutes?
Sure, please.
Yeah. So I just wanted to first thank all the 5 speakers for giving us a snapshot of the work that was in their thesis, and for giving the really wonderful and nice clear talks. Now, as I was scrolling through the list of participants, I realized that now there are not many that perhaps knew Rahul, and therefore I thought that it is only appropriate that I say a few lines about few words about our friend Rahul Basu, who passed very untimely, and he was a perturbative QCD enthusiast. He has done some interesting works in perturbative QCD, and worked with one of the big bosses, did his PhD with one of the big bosses, that is George Sturman in Stony Brook. And he had been working in the Institute of Mathematical Sciences until his untimely demise. Apart from his interest in physics and work in physics, I think we all knew him for his enormous interest in the community activity in physics, as it were. And he was always he had lectured in many circ schools. He was a tutor in some of the circ schools, and he was quite popular with his students. And for many of us, he was also very well known for both his Indian and foreign collaborators. He was well known for his gourmet tips about where to eat and what to eat. He was a great art and food connoisseur. And actually, my friend Nilima, in fact, said this award in his memory, as she said, and I should actually thank her, I think, on behalf of the entire high energy physics community for having made available the funds for this really nice and competitive award. And having been associated with this award right from the early days, I can tell you that every time the job of selecting the best thesis is becoming more and more difficult. And now, we have usually a very large number of theses which reflect a very good and high quality research. And then the decisions are made, of course, on a combined evaluation of the quality of the research, but also of the presentation of the material, as well as of the overall perspective that the thesis itself presents. And therefore, most of the time, if the chapters where we look at is that, when you write a paper and when you write a chapter of thesis, things are quite different. And I can tell you that all these awardees that we have chosen have actually done a great job and making the thesis a self-standing, self-sufficient document. So again, I end this by first thanking Nilima for making this award possible, because I think this actually galvanizes the young community and helps us identify the future young leaders in the community in the form of all you awardees. As a matter of fact, I may mention that one of the first awardees, Diptima, is one of the conveners of one of the sessions in this DAE symposium. And I'm sure that all of the awardees are going to come back and contribute for the enrichment of the high energy physics community. And second, so I would like to thank Nilima especially for this, for having instituted this award. I would like to remember our good friend Rahul on this, and I am sure that he would be very happy and satisfied by seeing the standard of the thesis that have been presented here as the recipients of the award, as well as the honorable mention. And I would like to thank the organizers of this DAE symposium for having made this slot available. So Vedang, now over to you.